In this video, I'm going to introduce how I technically designed the collaborative mind map with respect to its architecture and some core algorithms. Well, the first thing I did was to define a model that represents the workspace. Here, I defined the model as a hierarchical structure, which includes the following types of elements: workspace, the root of the structure, as well as doc, page, echo, selection, and clip. The workspace is the root level container, aggregating and organizing a set of docs and their derivative contents. On a client, all the elements you see are in the region of an extended area of a workspace, which incorporates all the chosen elements of it. A doc element is an element that logically manages a source PDF file and all its pages. A page element, on the other hand, is something visible compared to docs, and manages all the annotations and interactions that you perform on a specific page of a document. In terms of the visible areas, the areas where the current pages of the source PDFs are rendered are the areas of the page of the docs highlighted with orange boxes, while that include all the extensions are called their extended areas, highlighted with blue boxes. An echo element is a content block comprising of your question and the AI response, and it can attach to a page or another echo. Here is a visible example of the area and the extended area of an echo, pretty similar to how a page works. Selections and clips are simple elements. Selections are texts that users select to ask questions, while clips are images that they capture. Here is the architecture summary. I implemented the server with Spring Boot in Kotlin language, running on Java Virtual Machine, and web client written in TypeScript, running on Node.js and React. And it also provides the feasibility to implement other clients on different platforms and systems. So first of all, we have a server running, and a client of whatever type, sending a request to create a workspace. Inside the server, a new workspace will be created as a file, and the ID of it will be returned as a response. Then, the client subscribes to that workspace using WebSocket. What the server would do is opening the workspace, which technically loads the workspace into a cache database, and returning the workspace structure back. Now the client has the structure so that it can render and show it. Since the application is collaborative, there could be other clients subscribed to the same workspace. In response to these subscriptions, the server would directly return the workspace structure because it's already in open status. And these clients could render them locally as well. When the user performs an operation on any of the clients, an action message would be sent to the server. After a bunch of operations occur on the server that I'm going to talk about later, series of events would be broadcast to all the related clients to update their local models. When the clients disconnect from the server, the last disconnection would trigger the workspace closure, where the structure in the cache database would be saved to a file. Technically, on receiving a request to create a workspace, protobuf is used as the format to create and store it. On the other hand, on receiving a request to remove a workspace, it is ensured that it has been closed by checking the cache database before deleting the file, and all the resources such as PDF files and images would also be cleaned. This diagram illustrates how the workspace is opened and closed. When a client subscribes to a specific workspace, let's say if it is the first client that subscribes to it, we open it, otherwise we don't. And when a client disconnects from it, let's see if it's the last client that disconnects from the workspace, we close it, otherwise we don't, because it's still in use. To avoid thread conflicts, multi-level locks are designed to ensure that instructions run in order. And to align with Spring code patterns, I encapsulate the code in controller and service classes. To process user interactions, I have a blocking queue collecting user actions requested from the clients, and a history that maintains what the users want to do and corresponding modifications in the workspace. Basically, there are 3 threads participate in the process. The first one is an HTTP thread that collects user actions and puts them into the action blocking queue. The second one is an action interpreter thread that monitors the queue constantly and gets the records and uses an interpreter to generate events in an asynchronized way using Flux. Every action it processes would be placed in the history, and every event emitted by the interpreter would also be stored and connected to its corresponding action. The third thread is the event processor thread, which monitors the history to find the events that haven't been applied and apply them to the cache database and broadcast them to the clients. Now let's look at the interpreter. The responsibility of it is to generate modifications upon receiving a user action. For example, when a user intends to add a PDF into a workspace, they would send an adding doc action. What the interpreter does is generating an add doc event which adds a doc element to the model and a workspace update gaps event to update the gaps field of its parent. These 2 events are called forward events, meaning that they perform what the user intends to do. Meanwhile, 2 backward events would also be generated, which reverse the impact, and they would be applied when the users want to undo what they did. There are quite a few actions. Each of them would be interpreted as a series of events. When the user asks a question, it would be sent to ChatGPT. Thus, it would emit events on receiving every chunk of the responses from OpenAI. When receiving a chunk, the related events would be put into the place and mark the history dirty. The event process thread checks every dirty history record for processing. Here is an example how the action interpreter and event processor threads work. Let's say initially the history was blank. Then, monitoring the action blocking queue, the action interpreter thread initializes the first line adding doc in history and moves the line cursor after it. The interpreter returns a flux to be subscribed, which emits a pair of forward and backward events that would be put in the event lists of the line. The event cursor remains prior to all of the events to indicate that all the subsequent events haven't been applied yet. The event process thread runs and collects all pending events. All the lines before the line cursor are expected to be committed, which means their forward events should be applied, and all the lines after the line cursor are expected to be rolled back. Now it moves the event cursor to the end of the list to indicate that these events have been applied, and apply the events to the cache database and broadcast them to the clients. In terms of an undo action, the action interpreter thread doesn't put any new item into the history, but just move the line cursor one step backward. The event process thread makes sure all the forward events before the line cursor are applied. In this case, it's empty. And it also makes sure that all the backward events after it should be applied. In this case, it's event remove. And it does the same stuff, applying and broadcasting. For a redo action, the only difference is the line cursor would be moved one step forward. The event process thread ensures that every forward event before the line cursor should be applied, which is event add doc here. And every backward event after it should also be applied, which is empty here. And apply and broadcast the collected events. Lastly, how is an event applied? Well, there's an applier object that converts the event to a database object and performs insert, update, and delete on the database using JPA. And events should be idempotent, which means applying the same event more than once doesn't cause side effect.